All right, so today's notes are on logarithms as inverses. Our content objective is to write and evaluate logarithmic expressions, and our language objective is to define logarithms by their relationship to exponential equations. So let's start by doing that. So logarithms calculate the exponent needed to get a specific value given the base, assuming that our base is positive and not equal to 1. So again, to put that in a different way, logarithms calculate the value of an exponent. So they tell us if we have an x or a variable in our exponent, logarithms allow us to calculate that value. So if I wanted to figure out 2 to what power will give me 7, I can use logs to do that. So to get to that point where we can actually do that, let's start by defining log. So if I have log base b of x equals y, that can only be true if and only if b to the y equals x. So again, I'm going to use some terminology here that we're going to use throughout the rest of this unit, so I want you to make sure you're paying attention to this. So our base of our log is this subscript here, so notice that it's smaller and a little bit below the log. That's the base of the log, and that's always going to be the same as the base of the exponent. So b is the same as b. The base of your log is the same as the base of your exponent. As I mentioned before, logs equal exponents, so the exponent in my exponential equation is what my log is equal to. So here y is equal to y, so logs equal the exponent. So bases are the same in both, logs equal the exponent, and the argument is this last part, it's what's inside the log. The argument is what is originally equal to the exponent. So what's in the log is what's originally equal to the exponent. Equal to the exponential expression. So again, these are the words. Base is the b, x is the argument, y is the power or exponent. You can use either term. So as I mentioned before, you can do things like calculate x if you were trying to figure out 2 to the x equals 7. So the way I'm going to do that is rearrange my exponential equation into a logarithmic equation. That's how I'm going to isolate my variable in my exponent. So I'm going to do that by determining my base. So my base here is 2. My exponent is x. And my argument is the only thing left. So that must be 7. So then I'm just writing this in logarithmic form. So I know log, the base is always the same as the base, so base is base. The argument, what goes inside the log, would be 7 because it has to be equal to the exponent. So as you can see here, I've successfully isolated x by rewriting it in logarithmic form. So log base 2 of 7 is equal to x. So I'm going to do one more example. This time there's no variable, so I want us to figure out how I could write 100 equals 10 squared in logarithmic form. So again, this is an expression we know to be true, and I want to just practice rearranging it. Just a reminder, logs equal exponents, so I'm going to define my base, which here is 10. So the base is always the number being raised to the power. My exponent here is 2, which leaves the argument to be 100. So when I plug that into logarithmic form, I have log base 10 of 100 equals 2, because it has to equal the exponent, base is the base, and the argument goes inside the log. One other thing is a log base 10 is called the common log. So log base 10 is the common log, so you can write that without the 10 in the base, just log 100 equals 2. So if there's no base written, it's assumed to be a base 10. So in this situation, we didn't have to write this 10 here. You could just write log 100 equals 2 because the common log is a base 10. So I want you to try the next 2 quick checks on your own. Pause it if you need to. I'm going to go over them now. So I'm going to abbreviate instead of writing out base power argument. My base here is 3. My power or my exponent is 4, and my argument is 81. So I'm going to write log base 3 of 81 equals 4. So log base 3 of 81 equals 4. So the exponent always goes here. Base is the same, argument goes in the log. So here, base is 3, power is 0, argument is 1. So I have log base 3 of 1 equals 0. So again, what this is saying when in log form is the 3 to some power, to what power gives me 81, and whatever it is equal to tells you what power it needs to go to. So 3 to the 4th equals 81, 3 to the 0 equals 1. That is what those logarithmic equations are saying. So I'm going to flip the page for a couple more things. Next one I want us to rewrite in exponential form. So go the other way. So try it, pause it, do it on your own. I'm going to go over it now. So again, I know my base is 3, my exponent or power is 2, and my argument is 9. So I'm just going to rewrite this in exponential form. My base is 3, my power is 2, it would have to be equal to 9. That makes sense because 3 squared does indeed equal 9. The other thing I do with some of my classes that can be helpful is what I call the snail method, or some of my classes have renamed Gary. So you take the base, you pick up the exponent, you equal the argument. So it makes kind of a snail shape. If that helps you, you can use that as well, or you can just define the different parts. The next one, I have a base of 2. I have a power or exponent of 4, because logs equal exponents, and then I have an argument of 16. So that means that 2 to the 4th would equal 16. And that would be my exponential form of that equation. All right, so we're not just rewriting between exponential and logarithmic form. I also want us to practice evaluating logs. And so this is going to require that we convert between the two forms, which is why we did that first. So first thing, or what we're going to do in this first example is find the value of log base 8 of 32. The way I'm going to have us approach that is to start by writing it as an equation instead of just an expression. So this is an expression you're being asked to evaluate, but for the sake of evaluating it, it can be helpful to rewrite it as an exponential equation. And to do that, you need it to be an equation from the start. So I'm going to rewrite this in exponential form. So I know my base is 8, my power is x, my argument is 32. So I have 8 to the x equals 32. So you might say that's not really helpful because now our x is not isolated, but this is where our laws of exponents come in. So remember how I've told you these will never go away? They're not going away now. So I need to rewrite both sides of the same base. You may remember doing this sort of thing in our last performance task. So now we're going to rewrite both sides of the same base. I know that 8 is the same as 2 to the 3rd. And then the x that was there has to stay there, so it's actually 2 to the 3x. On the other side of the equation, I know that 32 is 2 to the 5th, so I can rewrite 32 as 2 to the 5th. I'm just rewriting both sides of the same base. Now I have the same base on both sides, I can set my exponents equal. So I can rewrite this and say 3x equals 5, because the only way this equation can be true is if my exponents are equal. Then I just solve for x by dividing by 3, and x is equal to 5 over 3. That would be my answer. If you wanted to check your work, you could. You'd plug it back in. Does 8 to the 5 over 3 give you 32? So 8 to the 5 over 3, that becomes the cube root of 8 to the 5th, which is going to be 2 to the 5th, which is 32. So it checks out if you wanted to make sure it does. So now I want you to try to evaluate the next two on your own. So pause it again if you need to. I'm going to go over it now. So I'm going to rewrite this, or I'm going to rewrite these as equations to start. And then I'm going to rewrite them in exponential form. I'm going to skip the process. So if you're not sure how I did that, go through, write your base at power argument, figure out how I got there. But again, 5 to the x equals 25, I rewrote it in exponential form. Now I'm rewriting both sides of the same base. I know 125 is 5 cubed, so I'm going to set my exponents equal. X is 3. Next one, again, I'm going to rewrite in exponential form. 4 to the x equals 32. I am going to rewrite both sides of the same base. So I know 4 is 2 squared, and the x is still there, so 2 to the 2x equals 2 to the 5th again, so same value for your exponent. And then you set the exponents equal. 2x equals 5, divide by 2, x is equal to 5 over 2 or 2.5. All right, we're almost on this set of notes, so I'm going to flip the page for the last thing I want to talk about. So these notes were titled logs as inverses, and I want to sort of connect that in a way that may make more intuitive sense or make some more sense to people in a different way. And that's with graphing. So I want us to graph f of x equals 2 to the x and its inverse. So we're going to start by making a table for the exponential function. So again, 2 to the negative 2 is 1/4, 2 to the negative 1 is 1/2, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So I really quickly filled out that table. If you're not sure how I did that, go a little bit slower, plug them in, see how I got there. Now I'm going to find the inverse of this function. So this ties back to what we did last unit. So I'm going to rewrite f of x with y. I switch x and y, and then I'm going to solve for y. So to solve for y, I'm actually going to use my log form. So I rewrote it in log form. My base is 2, my argument is x, and my power or exponent is y. So that's how I find the inverse. I switch my x and y. I need to isolate y. I use my logs. And now I have the inverse function. So I replace the y with the inverse of f of x, and I have my inverse of f of x function. What's useful here is I can actually also use my table to fill out my other table. I don't need to evaluate every single log. I can just plug in the y values or the range of my previous function into the domain here, and same and vice versa. So now I have my original function and my inverse function based on these tables. So if you ever need to graph a log, find the exponential table, switch them, graph your log. So I want to now sketch this before we talk about the domain and range. So for the first function, I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. So I'm going to sketch this exponential equation, and now I'll label it so we know which one's which. There's my original function. My inverse, again, we've already switched our x and y, so now we're just plotting it. So at 1/4 on the x, I have -2 on the y. So that's going to be about right there. -1, or at 1/2, I have -1. At 1, I have 0. At 2, I have 1. And at 4, I have 2. So you can see what a logarithmic function looks like. It is again reflected over the line y equals x, which we know about our inverse functions. So it's just flipped over that line. There we go. The last thing I want to talk about is the domain and range that I mentioned before. So the domain of my exponential is all real numbers. The range, since there's no k value, I know the range is going to be y is greater than 0. So for my inverse, all I'm doing is switching those two things. So my domain is going to be x is greater than 0, and my range is going to be all real numbers. So again, you can find all the information you need to know about your logarithmic function by knowing it's the inverse of your exponential. All right, that's it for today. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.